All right, Mark Kotanchek. I'm with Evolved Analytics, and we have a software product for data analysis, data modeler, which we license, as well as doing consulting and related projects in that space. So one of the things, of course, data science and big data, this is the theme, but the reality is that the information content on data sets is generally, there's a lot of value to be gained from relatively small, say, million or less records, hundreds of variables or fewer, okay? So if you get into the modeling space, if you know that the system's linear and you know that its structure, then you want to use linear regression because that's the right technology for the situation. If you know the model structure and it's nonlinear, but you do know the model structure, then of course it's a nonlinear regression of parameter estimation sort of scenario. The big focus of machine learning is where I know which variables count and I know, but I don't know the model structure. That's sort of an open-ended analysis and very powerful. You're looking at a lot of tools there, neural nets, support vector machines, random forests, and also symbolic regression, which is the technology I care about. But our sweet spot for us is you just basically don't know anything. You have this big pile of data, and what's truth in that? There you really want to be using symbolic regression. Now, I have a bit of frustration because oftentimes, the drunkard looking for his keys under the light where the light's good, right? Not necessarily looking where the keys are good. One thing that's also important in the overall modeling process is it's a workflow. It's an iterative process to look at what counts, okay? And then you deploy the model, maintain the model, and if you just do one part of it, you're not really doing what needs to be done. Data in the real world is typically ugly because you've got correlated variables, lots of records. Maybe you have a fat data array, and we've got clients which are doing modeling with 25,000 variables. I could have long records. We've got, NIST is doing rheology modeling with, millions of records and hundreds of molecular descriptors. You've got erroneous data, you've got missing data. All these things sort of have to be handled automatically. So the key point here as we go through is that symbolic regression is really a hypothesis generator. The conventional strategy in statistics is to propose a hypothesis, see how well it fits, and if it's not good enough, then you propose another hypothesis. Well, that loop is very human intensive, and it also imposes restrictions because, unfortunately, God doesn't know that the world is a second-order polynomial with no cross terms. So what we're going to do is we're going to have this primordial soup. We're going to throw into this vat the data and some operators, plus, times, square root, whatever, and let it evolve. And then we're going to get lots of solutions, lots of hypotheses generated, and have it come out. Okay. So for this analysis, I'll be using a chemical reactor data sanitized from the consulting project we did. They were having problems with the quality control metric, and so we have 125 variables, 3 months worth of data, 2 data sources. One was the gas chromatography from grab samples. So the chemists care about that because it gives them insight in terms of what's going on. The production engineers have the PI system, the process information system, and that's useful from the perspective of what to do. So on that note, we're going to shift over, launch the GUI. So we have a notebook interface that we developed. So it's standard function package. So this is useful to assemble custom workflows. But we started, couple years ago, started working on a GUI because of the inability of people to actually hit Shift Enter. And you know, truth be known, I've come to prefer it as an interface because you know, it winds up being this interactive. You're bouncing around through the data. Here's the data. Let's go take a look at these characteristics. The data summary table sort of lets me look at characteristics on an individual basis, how numeric it is. You know, of course, you need to be able to plot stuff. And here it's you know, 125 little plots there. The data completeness map lets me look and say how complete is it. In this case, I have some missing data and a few non-numeric columns. But the real thing here is the correlation chart, and this is the thing, the bugaboo, because you know, your conventional assumption is that you've got uncorrelated inputs, right? And you have to be able to deal with all this stuff in blue, dark red, or they're, you know, highly correlated or highly anti-correlated, and you have to be able to handle that stuff. So what we do, I'll just do a quick, well, 30-second modeling. I've got some redundant variables in there. You can see here that you can add comments to your modeling rounds. And this is one of the things, you're iterative. You're slowly attacking truth. I'm going to take those 125 variables, and I'm going to chip away at that and try to develop understanding and insight as I go. So what I've just done is I've initiated a 1-minute modeling run, and what you see here is going to be 4 traces because this is a quad-core laptop, and so each model search runs independently. So so you spawn off these subkernels and they go. I mean, I've got clients running as many as 200 subkernels simultaneously doing model searches. But what you're seeing then is very you know, algebraic models, so human interpretable models, and that's one of the advantages here is you're able to say, I can mine. I've got all these models, but now I can go in and mine them. And what we're doing here is this plot here is error, 1 minus r squared, and complexity. So we're rewarding during this evolutionary search. What's a good model? A good model is simple and it's accurate. So that's really the constraint that we're throwing on into the process, and it's chipping away at that. And what you've seen here in this trace, very short trace, is over time good models get rewarded, and you're building up an interface. So let's analyze some models. So I've got 32 modeling runs that I'm going to load. And what we see here is this trade-off. Now this point here is the knee of the Pareto front, is what we call it. So this is sort of the sweet spot of where I want to develop models. But let's take a look at some other tools. So there's 4,000 some models that we had done with, you know, a whole bunch of 3-minute modeling runs. So the model dimensionality table is important because it's telling me how many variables do I need for a model. And it'd be up. Okay, so here let's make this a little larger so you can see it. So we've sort of got this distribution of models. So where is the sweet spot? Well, part of the problem is, in this case, I was looking at all the variables, but I really, I want something with 100, complexity of no more than 100, and 70% R squared, and I'm going to sit here and take. So there's models up here in the upper right-hand corner. I don't really care about them, so I'm going to trim off and take 50% of the models closest to the Pareto front. Okay, and that gives me sort of this banded structure. And these are the ones that are sort of interesting. I can explore. Now I can come back to say, well, for my candidate models, where's my action? And now this here is. Someplace between 3 and 5 models is sort of 3 and 5 variables in my models, sort of be a handy place to be. I can look at, this is looking in at various combinations. I can sort of mouse over and see what sort of models have been developed in there. And remember, starting with 125 variables, so it's reasonably impressive that you can chip this thing down in such an efficient manner. I can look at my variable presence. So this is, which ones have emerged to the fore. And you get, even though we've started off with all these really correlated inputs, we've focused very quickly. Now, each of the model searches has followed its own path. So we do get different results. So what this is doing is breaking the modeling into its independent searches and saying how prevalent is a given variable in that modeling run. So we're getting an idea of substitution effects. So what the potential is for replacement. Because when you're doing something going into a plant, I have choices of sensors. I mean, is a pressure sensor more reliable than a temperature sensor? Probably not, but so I've got different things. Or I can use a grab sample. In this case, I've got a mixture of GC measurements and things. Well, grab sample, that's a few hour delay to get that data in here. Would I rather have something that I can use directly? Okay. So let's hop forward and retrieve. I did some modeling. I'll turn that off. Did some modeling, then strictly focused on the gas chromatography information for the chemist's sake. That should read. Okay. So here I'm going to look at this information. Again, the model dimensionality is telling me sort of trade-offs. I want to go. Okay. So here, so back to the model, so here's the substitution effects that I go. So 3 variable models, I can use maybe small GC4. Now, of course, with the real data, this would actually be the chemical name that would pop up. It's extracted from the file. But this is how I can look at variables. I can go in and I can take this variable set and I can mine it because it's an algebraic structure. Now, in the evolutionary search, what happens is a nugget will happen, maybe the difference of two variables, the ratio of two variables, some sort of structure. And this structure adds value. And the value that gets added then is, it gives you insight. Say, oh, that's an interesting relationship. What does that mean? And this is where we're extracting insight. So, but what it can do then is I can say, the difference between chemical 44 and chemical 50, I'm going to add that as a meta variable. And so that then appears in the generate models, and I can have these meta variables I can use essentially as nuggets, as structures in subsequent modeling rounds, and say, do they apply and what's the value? The other thing that I can do is I can look at variable combinations. And for that, let's go to round 6. There we go. So we'll go look at what's available for the process side of the world. In the variable. All right, so here we're looking at, oops, loaded the wrong data set. Oh, yeah, if I could read, that would help. All right, so we've got different model sets that I've got, but say let's look at our model. So variable presence chart. So what I can do here, though, just as an aside, I can go in and set a threshold of saying I want to focus in on variables which are in at least 20% of the models, and then I can name that as a named variable set, and then exploit that in either modeling where I'm focusing in on those variables during the model search, or filter directly based on those. But what I want to do first here is variable combination table, and I'm going to sit there and say I want to restrict things to models with no more than 4 variables. Okay, what is my impact of having those variables? Are there combinations that I might want to use and explore and go forward? And here you're seeing the source and a couple temperatures, and it's oftentimes you'll see something interesting there and want to build off that very small subset. Now let's move to sort of the end game, and I'm going to load in. I did a bunch of modeling with only 4 variables. So I chopped this down. I got 4 variables that I think are candidates. And this is where the plant engineers come through and have preferences on what they'd like. So how good are these models? Well, I've got a couple options here. I can just turn the model picker on. So the model picker lets me select a model that's been developed and sort of look at its attributes. So here's most people would choose a model. Now we don't want to choose a model because we've got all this diversity. We've got all this whole really different worldviews of the data. We can exploit that and build an ensemble of trustable models. So we can take this whole collection of, they're all good, right? They're all candidates in the sense that they're simple, they're accurate, they're meeting our thresholds in that fashion. Let's get a diverse set of them and get a diverse set, and then they're going to together. When they see a spot and parameter space where they've had experience, they're going to agree because they're all good and trustable. However, when they're exposed to new regions of parameter space, or the target system is changed in some fashion, then they're going to diverge because we've chosen them to be unique. But so anyhow, you can have the standard sort of issue prediction plots of models and trade-offs. But let's go to this ensemble that I've defined, and that's just clicking a button to get that. The ensemble prediction plot then is the prediction of truth versus reality. Now what you see are error bars around each prediction point. So you get this sort of spread that's coming into play. If we use the response plot explorer, now what we've got is, from given point in parameter space, so high dimensional parameter space, I can sit there and say what is the effect of changing variables relative to that space. Now here we've got two temperatures, and they're in a distillation column, they're coupled, right? So we have coupled variables. So if I start changing temperature 20, so now I've got my tray, my tray, in a different spot. Now what you've seen here is at that point in parameter space, now I've got uncertainty that's been introduced in my model. If temperature 22 starts riding up, getting back to its sort of natural alignment, then that uncertainty goes away. So we're getting this trustability factor that's very important. Now I'm just about out of time. I will say then that another thing that you can do that's very important, and it's not in the GUI, but it's used by a number of folk for using the notebook interface, is I can take that trustability and say, I want to do active design of experiments. So I've got a difficult to measure system. I'm going to go in and take a handful of data parts, start building models, start saying which factors are important. So an example is catalyst discovery. I'm going to take a blob, expand it into its 2,000 molecular descriptors, which descriptors are mattering for the performance that I care about, and then I can go in and say, okay, this is where I think there's an optimum. Go explore that region in parameter space, sort of standard optimization strategy. But what I can also do is take my ensemble and say, where are they disagreeing? Because where they disagree is where's the most valuable next nugget of information I can collect. And so that is very key to this active design of experiments. And so now you're covering, you're adaptively sampling your operating regime and really trying to nail things down.